Hello and welcome. In the first video we discussed about the basics of simple harmonic motion, and in this video we are going to discuss about the maths of simple harmonic motion. Simple harmonic motion follows a similar pattern to that of a circular motion. For example, the figure on the top shows a simple harmonic motion of a simple pendulum. Figure on the bottom shows its corresponding circular projection. So when the green arrow moves from A to F, the pendulum completes half of its single oscillation, which corresponds to a half circle in the circular motion. Although in reality pendulum is not moving in a circular motion, its motion is the projection of motion in a circle. Because of this reason, we can use the equations we used in circular motion to describe the behavior of a simple harmonic motion. Now let's consider a moment where the pendulum is at B and has displaced by distance x from the equilibrium point O. We know for a circular motion, angular velocity omega can be defined as the rate of change in the angle. For one complete oscillation or one complete circle, the angle is 2 pi. We know the time taken to complete 2 pi radian is equivalent to the time period t. So now we can write the angular velocity as 2 pi divided by the time period. And we also know that time period is the reciprocal of the frequency. So now we can rearrange this equation as angular velocity omega equals to 2 pi times the frequency. Now let's derive the equation for the simple harmonic motion. First, let's derive the equation for the displacement. When the pendulum is at A, the projected distance OA is equal to the radius of the circle. When the pendulum is at B, the projected distance is OB, which is equal to the x, and we can call this as the displacement. X is found to be equal to r cos theta, or the horizontal component of the radius. And we know that angular velocity is the rate of change in the angle. Therefore, we can rewrite the displacement x as r cos omega t. So if the amplitude of the simple harmonic motion is capital A, we can write the displacement equation as a cos omega t. Now let's derive the equation for the velocity. Velocity is defined as the rate of change in the displacement. Since we know the displacement is given as a cos omega t, we can differentiate this by time t to find the velocity. And since we know a is a constant, we can keep as it is when differentiating. The derivative function of cos omega t with respect to time t is omega times negative sine omega t, and we can now take the negative sign to the front of the equation and write the velocity equation for simple harmonic motion as negative a omega sine omega t. Now let's derive the equation for acceleration. Acceleration is defined as the rate of change in the velocity. We derived the velocity of simple harmonic motion before as negative a omega sine omega t. Since a and omega are constants for a particular motion, we can keep both a and omega as it is. The differentiation function of sine omega t is equal to omega times cos omega t. Therefore, we can rewrite the acceleration equation as negative a omega squared cos omega t. And also we know that the displacement is equal to a cos omega t. Therefore, we can replace a cos omega t in the acceleration equation with the displacement, and we can rewrite the acceleration equation as negative omega squared times the displacement. Now let's go back to recall the restoring force of a simple harmonic motion. Restoring force of a simple harmonic motion is equal to negative k times the displacement. This k is also called as the restoring force constant. Since we know that the displacement is equal to a cos omega t, we can write the restoring force F as negative k times a cos omega t. We also know that according to the Newton's second law, force is equal to mass times the acceleration. Therefore, we can write mass times acceleration is equal to negative k times capital A, which is the amplitude of the simple harmonic motion, times cos omega t. We can rearrange this equation and get as acceleration, which is equal to negative k divided by simple m times capital A cos omega t. We already derived an equation for the acceleration of the simple harmonic motion in the previous slide, and we can equate these two equations to find the restoring force constant k. By doing so, we will get an equation restoring force constant divided by mass, which is equal to the omega squared. By rearranging this equation, we get the restoring force constant is equal to mass times the omega squared. Since we know the functions for displacement, velocity and acceleration, we can plot them along the time axis. Displacement is a cos function, velocity is a negative sine function, acceleration is a negative cos function. Therefore, we can plot them as shown in the figure. If you found this video useful, please subscribe and like for more videos. Thank you.